Yeah, we're going to talk about Herbert Simon stuff today, right, Puss? Yeah? Yeah? Rich gets richer model? Yeah, we're going to talk a little bit about branding too. How to call your model a very clever thing. Yeah? So people will like it. And then how to not know about other people's models. That happens because science is big, but in some ways getting smaller. Okay, because we know so much things. Oh, yes, we know such much things. Oh, it's just very fun. Yeah, you love counting, right? Love the gamma functions? Oh, so much fun. A little beta function action. Maybe some. Yes. Limiting behavior. Very nice. Okay. Oh, not going to roll over. Yeah? What do you think about that? So it's Herbert Simon's great 1955 piece? Yes. We'll try to understand where these size distributions come from. It's one very simple story, and there are many, many stories. But this is one of the big stories. Yeah, there are going to be gamma functions, and some of those beta functions. Oh, I know, that's so good. I love gamma functions. Yes, it's a factorial on drugs. Yeah, so nice. Okay. But we're going to find out what happens in the real world, how things become things, yeah? All right, bye-bye. All right, so Vermont Dalek, it's pretty great. Yeah, there you go. Anyone know how to exterminate mold from inside a hard metal casing? Asking for a friend. And so there's all these other ones. There's a Republican Dalek. There you go, Republican Dalek. I don't know what's going on. If you make it the next door, Doctor, I will exterminate myself. All right, sorry. I mean, well done, humans. Really good. So that is sort of England's fault, as is many things in a way. All right, so good things. Cricket, for example. So we're at the, we went to the London Museum. There's a Museum of London, which is really well done. And so they had this little display of, the bikes you can rent in a lot of cities now. So there were a couple of waves of this, right? There were the ones that opened up and then all got stolen, and then they had a new system. And so now generally they're spreading. So places like New York City have it. Montreal's had this sort of thing for. So this is tracked, so they know where you take them from, of course, and when you put them in. So you get all this nice data, and this is a little visualization of, we saw an installation of this. But what happens is, I think it's just 2 minutes long. So all of these are kind of somewhat real time, and then they start to color in the ones that are near each other. Is that all right if I turn this off? Yeah?
So they had GPS on these guys?
Yeah, I think
they track the station you remove a bike from.
I think that's it. Yeah, that's going to be it.
But there's like things moving in between, which could be that, but maybe they're inferring.
So the white dot.
Yeah, I think they're inferring, actually. That's a good question. Maybe they're just taking a sort of a flow path.
Traces.
Yeah, I mean, these are, because the way they're moving is not, they're not following roads, right? They're giving a little gloss to. So you'll get that general flow path, and then I think, right, so you start to see the big structures.
So, I don't know anything about London.
Knowledge of London, yeah, I know a poor amount. I think this is Hyde Park, and I know there's a description in here on this page, this Atlantic page. I think that's what, so there end up being three main kind of groupings in the end. Manhattan is funny because at the bottom of Central Park, that's where they stopped. That's it. There were none above. So the Upper West Side is out.
Does not bicycle.
I mean, it does, but it's just not on the team for this one. Anyway, it's kind of cool. Lots of fun visualizations. So we're going to talk about this guy today. I'll link to this later on, Herbert Simon. This is his bio, but it's his little autobiographical piece. What do we want to do with this? Do we want the disturbing lights on? Fluorescent lights, great. Anyway, we're going to talk about him. Spent most of his career at Caltech, and did great things, and he was given a Nobel Prize in 1978 in economics, although he's not really an economist in a way. So he's a real forerunner of complex systems, actually, but kind of everything. And we'll get to that in a little bit. He, what's called behavioral economics, for sure, absolutely, yeah. So he thought about how people behave, which is a little bit of a novelty, right, in economics. Okay, so, I mean, there's psychology, but then we'll just call it, yeah.
We're robots.
Yeah, we're predictable machines, right. All right, so no doubt you've all watched the previous online slides. Yeah. Okay. Well, I trust you have. And you have an assignment due on that on Thursday, so we'll probably talk about that tomorrow at office hours. I'm excited to do that. So that was about how randomness and can give rise to these power law size distributions. In one example, I mean, we have to touch a lot of different things in this course, and that had a number of aspects to it, right? Randomness giving rise to order, and of course also these power law size distributions that we're so enamored with that we find even when they don't exist. All right, because we're good at science. Okay, we'll get to those problems later. And we had transformation of variables, which gives you a very nice, decent story as well, right? So you have a very reasonable thing like an exponential distribution, sort of thing you find lying around on the ground, or a Gaussian, and then you have a transformation between two variables, which is good. A little bit of Doctor Who theme in there, which is appreciated by the course tweeter, and that gives rise to power law size distributions as well. So now we'll get to kind of one of the it's a great battle actually between a couple of ways of looking at things. So there's a randomness aspect in these growth mechanisms I want to tell you about, and then over here is optimization. So whatever the mechanism for getting there, you have some sort of evolutionary process that optimizes things. Right? So the platypus being an optimal organism produced by biology, right? That's good evidence, yeah. So there's going to be some fighting between those two things, and as I'll show you, I mean, this is still being argued about, and this is work from the 50s. Still being argued about. It's a very fundamental thing. These kind of growth mechanisms happen all the time, and we're rediscovered all the time, too. I think we probably have come to the end of that in science. Like we know about them now. Across fields. All right, so these guys are in charge. Come on. This is dead. It's dead. It's dead. Okay. Bad thing. Okay, so there's going to be growth mechanisms, and that's Herbert Simon, this fellow I was telling you about. That's going to be his side of things. And then we'll get to Mandelbrot, who you've probably, if you've messed around with fractals and some other more advanced things, then you would have come across him. Okay, Benoit Mandelbrot. Terrible joke. Benoit B. Mandelbrot. The B stands for Benoit B. Mandelbrot. Okay. Right. Actually, not a bad joke. All right, so it's not mine. So I gave a talk at Oxford last Tuesday, right? And so this thing here, that's an Oxford comma, right? Yes. My title had an Oxford comma because I'm pro Oxford comma. All right, so I only realized after the fact, that's why I was allowed to leave without being killed. Anyway, so all right, so we're going to have this, and then we're going to have this optimization story, and we're going to see these guys fight each other, right? So this is going to be the quickening for you Highlander fans out there. There can only be one theory, and that's going to be quite amusing. So it's something that didn't play out on tweets, right? This is the 50s and 60s, but it played out in journals where they kind of argued with each other. All right, so random copying. So we've talked all about random walks, right? And it's a very simple thing, but it's additive aggregation. We're just adding things, and we forget where we forget what's happened before, except for where we are right now. Right. Random addition and subtraction. So, and the way we didn't have competition in this either. We just allowed all of these random walks to play out, and then we started to count them, right? And we counted some aspects about them, and in particular, this first return thing. So how many first returns do you get after 2t time steps? All right. Now, they weren't competing with each other, right? It was just letting everything happen. Now, the world, the universe is full of competition, right? There's only so much space for whatever it is. You know, the star to exist, literally, and, you know, Kim Kardashian or whoever's there's only so much space, attention space, right? Talk space, actually, it's talk, right? Fame is talk. Okay. So we're going to go to this random additive process. It's copying. There's an emulation process, which sounds very human, but of course is very biological. It's a nice algorithmic kind of thing. We can turn it into a sort of a physical model. We can play around with that. And it's going to have competition, right? These guys are fighting each other. So we'll apply, in principle, it is not the exact mechanism behind all of these things, but it is the sort of raw base mechanism to kind of understand. And then you have to go and figure out the details of real ones. But it does seem to definitely occur. And as I said, people are still arguing about this. So the data's been around there for a long time about these distributions, but some of the mechanism processes, you really have to have fine-grained data and the history of the system to be able to kind of get at that. And you have to do some clever statistics as well. So that's why perhaps that's lagged a little more. You need more data and you needed some cleverness as well on top of that. Okay, so words in books, the sizes of cities, the web, so how many links point you, how many, traffic, that sort of thing. Wealth of individuals. Now, not all of these necessarily follow Powell's, but they have very skewed distributions. This is scientific productivity. This goes back to the 1910s. It's one of the great sort of laws of bibliometrics, right? So some scientists produce much, some produce very little. Popularity, of course, in terms of sales or whatever it is, music, people, lots of different things. So that this story that I'm going to tell you is applied to. And of course we have competing mechanisms. So that's the thing, right? Again, the Gaussian, one big story, fantastic, everyone is happy. Here we just have lots of different stories. And you have to really figure out what if you like, exactly the narrative is of your system. So there are different kinds of mechanisms that could give rise to the same kind of external picture. Oh, it needs to be, that's all right. I'm not going to do it. It needs to be recompiled. All right, so, okay, so I'll come back to this later on, but I want to tell you about when we look at catchphrases, right? How do you brand your scientific theory? And we'll see it's been done pretty terribly until recently, and it matters. So you have Yule's work, and so Yule's attached. You'll see Yule, Zipf, Mandelbrot distributions, or Yule, Zipf distributions. They're talking about these things, just as we talked about Pareto distributions. Locker, as I said, this is a number of papers per author. So this is the 20s. I said 10s. This is the 20s. So Mandelbrot appears in 53 with it's a chapter in a book, very excitingly, kind of towards the end, but it's become inflated as a big piece. So it's an optimality argument for the Zipf's law story, for books and so on that they were thinking about. And the focus is very much on language, right? It's very much, and we'll go through it, but it's very much explicitly about language, right? So how do you, this is an information kind of argument, right? How do you encode what you want to tell someone else or tell others as optimally as possible? And what happens potentially over time with language evolving? Some funny stuff there. I mean, clearly language evolves, right? And so, but we'll see even back in this time, there's some responses to Mandelbrot stuff that says, there is no direction of evolution for language, axiomatically. Boom. No. But there's actually now, of course, beautiful evidence that that's not the case. So Simon, 55. So this is a fantastic paper. Has inspired all sorts of other things. And I'll tell you something about it down here in a second. But so he expands his story, right? It's not just about language. It's word frequency, city size, income, publications, and species. He's quite explicit about those 5 things, saying look how general this is. Right? We have these general laws. There must be some explanation that is, itself very general, applicable to lots of different things. I mean, these are ridiculously different things. Language, where people live, biology, right? Now, of course, this is also the way this is before DNA, right? So this is, this is based on our taxonomy that right? Platypus goes here, all right. I like the platypus. Let's see, so then we have 1999. So okay, I should have said this one. So de Solar price. And so this connects into Locker. This is about bibliometrics and so on. But so these are people counting, going through, looking at the number. This is really painful, right? So you get a paper out, you go through the citations, and you see which ones link. So that's really awful because when the web came online and a little bit later we started to put papers up properly, you start to be able to see what cited a paper in the future, which is spectacular, right? So you get a paper from 1972, and of course, something like Web of Science, right? You can click on everything that cites it, and of course Google Scholar does that fairly well. I mean, yeah, no, it does. So you can go forward, which is very natural, but very hard to do if you're in a physical library. I mean, that's a horrible thing to do. You've got your paper from 1923, it's in a thing, and then you want to find which paper cited. Awful, right? That's terrible. So but that's the sort of thing they, manage to. Of course, you just go through maybe a journal and look at which papers are cited back into that journal. Let's keep yourself from exploding and your graduate students from attacking you in the middle of the night. Does happen. We try to build a very nice family. Okay, so he takes, in fact, Zip's model and applies it to networks, because now we're talking about networks. We're talking about directed networks, right? You have your journal, your paper, which points back to this paper. Other papers point back to it, and you start to get this nice big directed network. All right. And now we have work that has opened up, in part, all this enormous work that's been done recently on complex networks. So it's Laszlo Barabazi and Reiko Albert are now thinking about the web, in particular thinking about Notre Dame. I'm going to say Notre Dame's website. Right? That's where they were. So that was the data set they had. And a few other things. They had the power grid, but it doesn't apply to that at all, not even close. This was published in Science. This was also published in Science. This is a big deal. This paper was published in Science. It's there. But there's a complete disconnect. Right? These things were not connected. And so it's a little awkward sometimes, but these are not connected. Or they weren't at the time, that's fine. But as I'm giving it to you now, it is all of a piece. People sorting out things in different places. We'll see the beautiful work in some ways was done by Simon. The mathematical stuff, fantastic. And there's some other work that's by a guy, Sid Redner, fantastic guy at BU, did some work at this time, looking again at citations, really nice analysis with a guy called Krapivsky. All right. So this is a little rough-hewn, but it gets out this story, right? The power law size distributions appear from this mechanism. It's going to be called preferential attachment here. It's kind of a rich gets richer, cumulative advantage, different names, and I'll connect those later. But a very simple kind of growth model. And we'll see that this doesn't really fit the data. This has some nice stories. Okay, so as I said, still being argued about. This is 2008 Physical Review Letters. That's, if you don't know, the premier journal in physics in the world. I don't care what Europe says. And this is coming out of, actually Europe, right? So this is coming out of Zurich. And it's a nice geeky thing to do. So you take the Debian Linux kernel and look at all the packages and see which packages reference other packages, right? And so this is for, they had a bit of a Toy Story thing going on. Obviously fans of Joss Whedon, anyway, who helped write it. I got to connect Buffy in there. So let's see, so there's Woody, Etch, right? So these are these different things. These Lenny, Sarge, so they were different releases. Okay. So I guess they're happy this Toy Story 3, they can keep releasing things. And this is the number of links coming in. So this is typical sort of thing we've seen before. This is a funny way of saying a complementary cumulative distribution function, which is the term we've used. So this is a number of links coming into a package from other links. Is that the right word? Package, yep. And yeah, so there's a power law size distribution. This sad little thing says gamma equals 1. It's mu, but it's what we've been calling gamma. So pretty stable, right? Growing, more packages. That's what's happening. So there's more packages. But so what they're able to do, and it's not shown in here, but what they're able to do, and we'll get to it later, is look at the growth of this thing. Right? So you can see if a package has so many links now, what's the chance of it having so many more links in the future, right? So if a city has 10,000 people, and 10 years from now, what's the chance of it having 100,000 or whatever, right? What's its trajectory? All right, so as I said, the first work is Simon's model, what I've called this random copying with competition model. So, political scientist, he did a ton of different things. There we go. And so early computer science work. He was interested in economics for sure. And if you want, you can read this bio. I'll mention it again. But he did all of these things. He wrote broadly. He came up with terms that feel like economist terms for sure, like bounded rationality, which is, okay, there's rationality and that's everything. And then he's saying, no, you gotta, so it's like, dividing infinity by a number or something. It's sort of trying to pull back from an edge which is insane, right? The cliffs of insanity. Let's have a smaller cliff of insanity. Okay. Definitely should do a Princess Bride themed lecture. Okay, so bounded rationality and satisficing, which is the idea that you don't optimize. Humans, right? Humans run around, they say, okay, this is enough. They go to the first store and this necktie is fine, right? About 1,000 publications, and he was a leader in all these things, right? So complex systems is actually something he talked about and framed and so on, really into computer science and algorithms, decision making, lots of stuff. Won the Nobel Prize in 1978, which is real tribute to the Nobel mission, actually. All right, good. Okay, so we're going to go through this model, right? And sometimes I say element, but I once said elephant, so I changed it to elephant. Anyway, no, I thought I said elephant, but I didn't. Okay, all right. So we'll talk about elephants. You can talk about anything you want. So it's going to have a flavor, so different flavors of elephants. We shouldn't eat elephants. I mean, color maybe. All right, okay, so it's going to be something. So try and imagine that. So we're going to have one that's going to, so it's random competitive replication. We're going to have one of these guys appears at time t equals 1. And then, and you can see how you can make this elaborate in all sorts of other ways. I'm going to give you one simple story, right? You could make the time that things appear, random, all sorts of stuff. But let's just have them as a clock and a new elephant appears, right? So lots of elephants. After t time steps, we will have t elephants. But they appear in two different ways. So with probably rho, it's going to be a new one, a new flavor, right? An elephant that you have not seen before. And so if you want to, and I'll say this again, I guess, but say if it's cities, for example, so that would be equivalent to saying someone goes to a new place where no one else is and says this is a city, right? And starts it off. Now, with probably 1 minus rho, our elephant is going to be of the same type of one that's existing, right? Right, so they walk in and they join one of the teams.
And you pick uniformly from the existing category?
So this is a subtle point, right? And so let's get that. That's right. So how do you pick? Okay. So we'll say that elephants of the same flavor, they form a group or a team, and the so I guess it's yeah. So it's said here. So what you do is you pick randomly from the elephants that are there. Don't worry about the teams or the groups. You just pick randomly from the ones that are uniformly at random. Yep, right. So if half of them are colored red, there's half a chance that you'll be red because you're going to select one, right? Right? Yeah. Yeah. Well, after you've done this.
Yeah.
After you've done this, good. Yeah, it's really nice. I mean, you can make some models here. I mean, the math is a little bit of fun, right? So you'll write differential equations with some probabilistic stuff in them. Fun. So this you can think of in very evolutionary type terms, right? So this is mutation and innovation, novelty, right? So a new thing appears, the platypus pops into being. Just kidding about evolution, obviously it doesn't exist. Replication and imitation. Right, so this is keeping the thing together, right? So it doesn't blow up. Yeah, like I'm going to go live in New York like everyone else. This is what people do, you know. Okay. And so it's, you know, it should be appealing at least in that sense, right? I mean, New York is a big thing. It's easy to see. It's not exactly that. The mechanism, as we've laid out here, would be you have to pick randomly from someone in the U.S. and then live in their city. A little weird, right? Because it's like it's a Steve Martin film. What is it? The Jerk, I think. Where, do you know this one? Where he said like how much worse could his life get, and then it flips to a serial killer who's just going through the telephone book and goes and points to his name. And, you know. And then it goes back, and then a little later that guy appears trying to kill him. Anyway, so, but that's basically how you'd have to do it. You know, just go pop and pick that person and say they live in St. Louis. Okay. That's a little weird. Immigration story, it's not kind of that bad. Did you?
I was just wondering, so this, the forming a group thing you have at the end there, is that, never mind.
I have a drawing of it in a second, but yeah, the idea is if, all the ones of the same flavor, the ones that are colored red, for example, we make a group, at least we make a group.
Yeah, and you pick whatever same flavor that is that they form groups based on. Yeah, in this case colors, but I'm just thinking, you know, applying this to a problem. I mean,
yeah,
there's all kinds of things that.
There's some aspect about them. So the city is just where you live, right? So if you're writing a book, this is a terrible way to write a book.
Yeah.
And I'm sure it's on one of these pages, but basically you look at all the words you've written, okay, right? And then you randomly pick from one of them, and then you put it there.
Okay. Yeah.
And with probably row, you make a new one, right?
Yeah.
Okay. So that would be a pretty bad book. Yeah. But it's not a bad way of explaining the evolution of language, actually. So it's not that bad. So, you know, it's obviously wrong and rough. Okay, so here's our words one, right? So they appear sequentially. Probably row. The next word is new. It's novel. You've never seen it before. 1 minus row. It's a repeat. This again is mutation. It's innovation, if you like, and replication, imitation. Right? It's a terrible way to write a novel. Don't do it. So it's important to know how bad our model is. Okay, so, but it's again, as I said, a very essential kind of model of which then you would tweak it and mess around with it. Language is very tricky, obviously. We have some great work in our group by a student who went through this course and has some stuff that 5 papers that will come out in a year. Jake Worms, really fantastic. That really build on this model actually in a beautiful way because it moves to phrases. It's really fantastic. Okay, so here's an example. This is at some point in the evolution of our little primitive language, right? So I think this might help with your question. So there are 21 words that are out there, and they are grouped, right? So there are 4 these and 3 ands, and then 6 ooks, a couple of penguins. So at this point, if you have a new word, with probably row, it's a new word, so you just pick out a new word that's different to these. 1 minus row, you go to this thing and throw a dart at it, and your chance of hitting an ook is 6 out of 21, right? But a chance of hitting that ook is 1 out of 21. So that mechanism is really simple, right? You don't have to think, this will be important when we think about networks. You don't have to think, okay, this is a size 6, this is size 3, this is size 4, add them all up, roll a very complicated 21-sided die. Or I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 9-sided die that's biased.
Yeah.
That would be bad, right? The 21-sided die is much better because then you know, this is number 1, this is number 2, that's easier. But the 8-sided or 9-sided biased one, terrible. That's what that 1999 model of networks actually does, though. It does that really biased, weird thing. So we have to improve that at least. Okay, but so is this all right? No one, Terry Pratchett, it's just not. Okay.
Gotcha.
Okay, so Terry Pratchett, yes, all right. The P.G. Woodhouse of fantasy, right? I mean, he's fantastic. Or, Douglas Adams gone mad in a new world. Good, good. That's very important for your education as a human. Good. All right. So it's a rich gets richer story, right? Right? More ooks. The ooks are in front. They're going to do well. These guys are possibly going to do well, but they're a bit further behind. So this is actually going to draw out. They're going to get bigger. So there's randomness. So different ones could win, and you could, if you dial things up and down, like the chance of, if you've got this, so it's 6 out of 21, but maybe you make it 6 out of 21 to some power, like you really do play around with a weird die, right? Then that's going to change things, and we'll get to that later on. Right? You can have the rich get much richer, and the rich get a little bit richer. You can have different variations on this model. The elements, if you like, are competing with each other to be replicated. And it's just their size that helps them, right? Yep. So it's good to be first. It's a first mover type situation. You can add, you know, as I said, you can add all sorts of things. You can add death and so on, right? So the things just go out of existence, or you could, right? All right. So the competition between, there's a distinction here, this is sort of what you were saying before, right? So the competition between the individuals is random. The individual words on the previous slide is random. The competition between the groups is non-random. That's the weird die. So selection on groups it has a size bias. You can say it like that. Bias by size. Good. This is easy, sort of. Sounds easy. And we'll come back to it. I've mentioned it a few times, I guess. But so it sounds easy to have that random selection, but it's a bit funny to randomly reach into a system and pull one thing. Okay. But we'll talk about that later on. I mean, it suggests you don't have to have any knowledge of the system. But yeah. All right. Okay, so let's do a little bit of the analysis, and you'll have some work to do to improve it after that. So we get one new thing per time, right? So we have t elephants after time t. And the number of distinct flavors grows at a rate rho, right? So there's a chance rho, which is typically kind of small. I mean, in principle, it can be anything, but typically kind of small. And I said we can add these things as well. So we can have elimination. We can have group things change, right? So they could change their flavors. We could change the innovation rate, right? It may decay after some time. And this more complicated thing, which could be this differential selection based on group size, right? So that's the rich get much richer, or the rich get a bit richer. All right, lots of other things we can change around. But this is the basic story. Okay, that's definitely harder. All right, let's do some things. So k sub I is going to be the size of group I, right? So it'll be flavor I, group I. Yep, and then we'll talk about this piece here. We want to figure this out. So there's a number of groups that contain k elephants. We want to know what this distribution is like. So there may be many that have 1, less that have 2, and then there'll be, the way you kind of see this, it's growing, right? So there'll probably be one group that has many elephants in it of the same color, but only one of those groups. Right? So again, so it's a bit like it's the same as there are many appearances of the word the. Right? The really is off on the end of the distribution. There are many words that appear once. Right. So how does this thing change with time? So we'll use Simon's analysis. Fantastic work. It's really, really nice. And he did some extra stuff in there to check stability and all sorts of things. Beautifully done. There was a very tiny mistake that you guys can surf over. All right. Okay. So a couple of things. So we're transforming into this. We know the number of elephants is t. We know the number of distinct types of elephant is rho times t, right? Because we have a fraction. Yeah, I know. Sorry. We have right? So if rho is a half, then we expect half of t, half times t, to be the number of distinct elephants. And the other half of the time we're copying, we're replicating. So let's get some pieces together. So this little piece will matter. So this is k times n sub kt. So this is the number of groups of size k. Multiply that by k. That gives you the total number of elephants that live in groups of size k. So that has to be t when we sum over k. Total number of elephants. So okay? Little piece. So this looks like a mean, right? This looks like the mean of this distribution. We'd have to normalize it, but that's part of it. Okay? So we have to think about how this thing grows. So let's set this up. Okay, so we want to see, so we have groups, so maybe there are 15 in here and 3 in here, and let's say 2 in here. So the chance of choosing this one is 2 out of 20, and the chance of choosing this guy is, what's it, 20? 3 out of 20, and this is 15 out of 20. But let's, let me think of it like this. So let's make it slightly more complicated. So we have, this is a group of size 1, there's a group of size 1, and a group of size 1. So there are 3 of these. So n of 1 is equal to 3. Right? N of 2 is equal to 1, and n of 3 is equal to 1, and then we have this n of 15 equals 1. And the rest of them are equal to 0. So we don't care, these are all different flavors, right? There's an elephants in here. And they have different flavors. They have a trunk, obviously. OK. So they have different flavors, but we're interested in the fact that they are just groups of size 1. Right? That's interesting to us. So our new, what we can talk about now is a transition. Like this one could become, if we get the next elephant, this one replicates, then it moves into a 2. Now it's a group of size 2. So we'd lump it over here. If we have a new elephant appear that's a new flavor, then it would be a group of size 1. So then we'd have 4 groups of size 1. Right? This one will move next to a 16. This will move next to a 3, so on. So we want to talk about what's the probability that we choose a group of size k. So we have this number, which we have to figure out. This is the total number of elephants in these groups of size k. Right? So 3 times 1, there are 3 elephants in groups of size 1. We're doing all right? Exciting. T elephants overall. So this probability then is k and k divided by t. Right? Okay, exciting. Okay, good. Okay. Good. So now we have the probability. We still have to, now we have to build either differential equations or difference equations of some sort to see how these things grow. But given the state of the system right now, that's how, and given we know this n sub k, which we don't, but if we did, then we'd be able to compute the probability. So we can write these things and we can connect them. Right, so how does this change? I just sort of mentioned it here. So we could have a group, an elephant that's in a group with k elephants. So if it gets chosen, right, there are 3, this is a 3, there are 3 elephants in here. So we're randomly choosing one of these guys. So we choose this one, and it goes boop and makes another one. And now this is a group of size 4. Okay. So this is it. This is this story. It's replicated. This is how we can change the number of groups of size k, right? So we could have a group of size k go to a group of size k plus 1, and we could have a group of size k minus 1 go to a group of size k. Okay, right. Sorry. So in this case, we lose one, right? We've lost one. In this case, okay, we lose one, and this happens with this probability. First of all, we have to have the probability that we're replicating, 1 minus rho. And then this is the probability of choosing an elephant in a group of size k from the previous slide. Okay, good. This is the other possibility then, right? In this second case, when we have a group of size k minus 1, move into becoming a group of size k, right? So it's a, yeah. So we have, at the next time step, we have one more. And that happens with probably, again, 1 minus rho. This is the probability that we are replicating an existing thing. And it's going to be k minus 1 and then nk minus 1 divided by t, right? We shift down 1 on the k. Yeah? Exciting. Yep. So it's slightly different. The normalization is just the normal, that's t is the normalization. That doesn't change. Right, so this is a probability that we selected an elephant that's in a group of size k minus 1. Good. So we're going to stick these things together. First of all, we'll deal with this one. So this is the new elephant situation. So if it's a new flavor, then we add to the groups of size 1. Or we have one of these guys get replicated and become a group of size 2. So this is the boundary, if you like. Right? The upper part just keeps going. So number of groups of size 1 increases by 1. And this happens simply with probability rho. That's it. So it's really easy. Okay? We could lose one, and that happens with probably 1 minus rho. Again, we have to replicate one that's already there, and it has to be that we've chosen, so this was 1 times n1t. Right, pk of t is equal to k nk divided by t. And so for k equals 1, there's a 1. It just disappears. This is a 1 cytomel. OK. OK. We all right? Nearly asleep? Just. I understand. It's 1:45. It's a cruel time. OK, so let's put them all together and consider this some sort of caffeine jolt, this page. OK. This is the expected number of, expected change in the number of groups of size k. Right? It's expected number. We're going to put these bits together. There's probably that 1 minus rho. That's probably that we choose a group of size k. This is for k greater than 1. Sorry, that's probably that we choose to replicate. So here's the probability that we replicate something in a group of size k minus 1. So that would give us a plus 1. So what's sort of hidden here is there's a plus 1 here, and there's a minus 1 here associated with replicating something that's already in a group of size k, making it a group of size k plus 1. So this is lose, gain. Right? And that's the expected change. One thing is changing every time, but we're going to make it expected. This is a bit of a sneaky bit, for sure. For k equals 1, we have a slightly different structure. So this is the number of groups of size 1, the unique ones. So there's a row, so there's a plus 1 times the probability of replicating a guy in a, introducing a new one. So it's a plus 1. Then there's a minus 1 times the probability of replicating something that's in a group of size 1. So this is going to shift out and become a, there's the 1. It's going to make it a group of size 2. Now, this is just one step, right? So we've got all these things here. This becomes maybe a 16, or we get another 1 here, or this becomes a 3 or 4. These bits are just happening one at a time. Yeah? So what we do is we say, well, let's imagine this happens a fair amount. And then we can kind of talk about what's happening to the 2s and the 3s and the 15s kind of over a longer period of time. So we do some sneakiness. Okay. Sneakiness. First of all, we want to say that we're kind of hoping, and we have to check for this later on, that we get a stable distribution out of this. It doesn't sort of, I mean, it's possible that it could turn to, soup in some way. We could get some distribution that's not stable, right, or not stationary. Stable is a bit funny. That doesn't hold its form. So we want this to be true, that there's some shape. So n, this just depends on k times t. So this distribution, whatever it is, right, if it's a bump, it's just growing with t. It reaches some form. So for us, it's going to be a power law distribution. So on the log-log plot, it's looking like this. So it's reasonable. You have to check for it later on. Again, as I said, nicely done by Simon. Classic paper, working through it. Good. So we can drop these expectations because we're imagining what's happening over much time is passing. There are many choices being made. Things smooth out. We have fractional elephants, which is a bit silly. Bad for elephants. And over large enough time scales, it's kind of OK. Right, so what else is going on? Well, so there's a little note here so that, right, so with nk equals nk times t, this is our assumption. If we divided that by rho times t, this is rho times t, right? This is the number of groups of size k. This is the and this is the total number of different flavors. Yeah, which is the total number of groups, right? So this is the number of groups of size k. So this is a fraction that is, it's just a little, yeah, that might matter. Yep.
You said Simon used this to model language?
Mm-hmm. I mean, the proposition, here's a really basic model. Let's just get this sorted out. And I'll show you how I'm going to get a power law size distribution out of it. And the ingredient is the innovation rate, right? This rho. So that's a very nice thing because you can measure that. So here's a really important thing, right? So a lot of statistical modeling is just, let's kind of describe it and get the shape out. Very, very important. The physics approach, generally speaking, is that we want to have a mechanism, right? So if we have fluid mechanics, we want to be able to measure, we have something that has viscosity in it. We can go measure that. There's an the charge of an electron, we'll measure that. That feeds into it, feeds into our equation. Right? These are things that in principle can be measured, right, in isolation. And so different systems that have different numbers, viscosity being a good example, changes the way the solutions work. Potentially dramatically, yeah.
Maybe we'll figure this out later, but little n sub k?
Yep.
T, I noticed like in further slides like that, we replace that later, but what is that?
So the idea is that it's going to hold its shape, and that the only thing that matters, the only way this depends on t, is that it just grows linearly with t. Right? So there are more things being dumped in all the time. Elephants, right? And so let's say the distribution is like this, and the area underneath it is t, because, right? So as t increases, it just keeps growing. So the shape doesn't change. So the little n sub k is the shape.
Okay.
Little n sub k times t is the shape. So this is, right, the number in each bin. Right, if this is n, 8, this is 8 here, and this will be, right, so this is n sub 8 times t, whatever that value is here. So n sub 7 relative to n sub 8, little n's, they right. Whoopsie. Okay. All right. So let's see how this cleans up. So we're going to say that this happens over a longer period of time, that this is basically the story where we're getting some, kind of growth in this little n sub n. And these big, this is a funny looking thing, this big n sub k here, did I throw it away? Yeah, no, sorry. Okay, this is n sub k at t plus 1. And so we're replacing n sub k of t, right, is little n sub k of t. And so n sub k of t plus 1 is n sub k times t plus 1, whatever it is, right? So that becomes little n sub k. So this is a bit funny with the brackets, and I guess that's a problem. I could change all that. Make them subscripts. That would be better. Okay, so it's going to be little n sub k times t plus 1. So this is multiplying. This is little n sub k times t.
You could just stick like a c dot in there. That'd be good too. Not
Comma t plus 1, right?
Yeah, but down below, like a c dot.
Oh, right. Yeah. Yeah, if I get them in the subscripts, that'll be better. Right. Craziness. Okay, so these things are simpler here, and you can see what's going to happen here. There's an n sub k times t minus n sub kt. This is going to clean off, which you're excited about. You'll get rid of that t there. And nice things are going to happen here as well. So this guy has been replaced by little n sub k minus 1 times t. Little n sub k times t there. Good things are going to happen, right? So we're going to group these together. These guys are canceling. Little n sub k here. Goody. These guys cancel. And so there was no t left in here. So now you've got a relationship that has rho in it. It has, so the innovation rate. It has the k, the group size. And it has the number of, the proportional version, right? This little quantity, the number of groups of size k. We have to multiply by t to get the real one. But that's sitting there, and then there's an nk minus 1. So now we can rearrange this to find a difference equation, right? It's not differential, it's a difference equation. There are other ways to do it, so you get a differential equation. Similar sorts of things. Okay. So this is just n sub k here on this side, 1 minus rho, and then we're going to mess around with these things a little bit. This is pretty simple. So this is k minus 1 times nk minus 1, and then, yes, minus k n sub k. So we need to combine these two guys, little n sub k, and this is going to be 1 minus rho times minus k times n sub k. We'll put all of that over here. So see if you can see that, right? So n sub k, that's this guy, times 1. And then everything times n sub k. So it's going to be put on the other side. So it's minus k times 1 minus rho. That's this bit. There was a negative sign, so now it's 1 minus rho times k. Plus. Cool? Cool, cool, cool. OK, so that is here. And then the bit that we leave on the other side is the one that's attached to n sub k minus 1. So we have 1 minus rho times k minus 1. So that's all here. So this is really pretty good. Now we actually have a ratio story, right? We have n sub k is equal to some ratio times nk minus 1. So we can telescope up, right? If we start with n1, we can get n2, we can get n3, we can get n4. And that's fun, right? Because gamma functions will appear. Factorials, and then gamma functions, which are factorials for grown-ups. And super exciting. OK. Oh, it's really great. You'll really love this. OK, so what you do is you telescope this out. You put in, this is the relationship between nk and nk minus 1. So then you can replace it with what it would be in terms of nk minus 2 and then nk minus 3. You see how the pattern works. You'll start to get factorials and things like that. And we'll talk about how it works. But it's pretty super duper. Really is nice. Very nutritious. So we want... OK, we're interested in how this thing behaves for large k. What are the large group size distributions like? What's the distribution like for large group number? Can actually be solved exactly, as I said, gamma functions and beta functions, good things like that. Assignment 3. OK, and if you just want to get at the tail, you can do some, that's a little extra experiment in messing around with things that help you sort of back of the envelope type behavior. So there's an exact solution, there's a back of the envelope thing that you can do as well. Okay, cool. So I think something we could do with this, I don't know if it's an assignment question, but I was thinking about making at least a script that you could play around with this, because one way to do this would be to make the tree maps. So tree maps, which aren't trees. Right, these guys. So it would be one way of it would be one way of you could have this dynamically evolving, right? Yeah. So this will be the number of elephants of a particular flavor, and then the next one. So you should see how this thing grows. Be one way of representing. I mean, you could. So the problem is, yeah, how do you arrange things so they don't hit each other? It's a bit tricky. I mean, you don't want to make up this algorithm. This one's been around for a while. You could do something more elegant with circles, perhaps, but like Apollonian packing style. But this is sitting there, right? So it would be what you should see is, yeah, that one starts to really dominate, and the next one, right. I think that could be a fun visualization. All right. All right, so here's the start of, I mean, we've got a long way with this. Now you have to figure out what, as I said, exactly what this little n sub k is. And it will depend ultimately on rho, right? And k is a number, so that's going to be some factorials and things like that, but it's going to depend on rho in getting there. And you know, it's some function of k. All right, so this is what you will find. You will do this. It's going to look like this. This is a bit of a funny way to do it, I suppose. with all this messing around, you see that eventually you can get this approximation. So it's 1 minus 1 over k to this little blob up here. And this is just some number, right? You've chosen this, whatever it is. Rho is 0.1. This is just some exponent. So we're going to rearrange it. This is really k minus 1 over k. Super exciting. K minus 1 over k. And that, if you look at this, this is this nk minus 1 is scaling as 1 over k minus 1 to this power. This guy is scaling in this way. Separate them out. Different ways of thinking about it. But basically, yeah, this is what we get out. So this is for large k. So it's a sneaky way of getting out large k behavior. So it's k to the minus gamma, which is, you know, yay. Right? Yay. Power laws. So you know, it's definitely an achievement. I mean, it could have come out. I mean, who knows? It could have been some other thing, right? You know, exponentials or something crazy. But it had to have a. It probably had to have a heavy tail. I mean, one might expect that. You know, you have to think about how you would have thought about this beforehand when you're doing your calculations. And of course, as you read this paper, which I encourage you to do, is you know, sort of a just so story after what, you know, like in the great tradition of mathematics. Right, so you know, thousands of monks have died to prove this theorem, and then you just get presented the theorem in 10 minutes. And it's kind of obvious that you would take this ridiculous path through the woods, avoiding the snake that would have bitten you, and this thing, and you don't know about them because, you know, you can't see all the dead monks. Right? Yeah. Okay. Mathematics should be taught in a much more, I don't know, like a survivor model, perhaps. I think that could work. Calculus survivor, or survivor colon calculus.
Like the original Survivor or like the new Survivors?
Okay, you can tell me about that later on. I don't think I have quite the refinement of knowledge there, but I probably am thinking of original, which is the one time I watched it. Yeah, right. Yeah.
And now they're doing a family.
Oh, really? No, none of that. No. Yeah. Oh, real snakes. Yeah. That you have to eat to survive. Yeah, right. Good stuff like that. Excellent. So gamma's, it turns out, so we have this exponent. It's fantastic. 2 minus rho over 1 minus rho. We can mess around with that a little bit. It's really 1 plus 1 minus rho. Not really. It's 1 plus 1 minus rho, so we can put the 1 minus rho over the 1 minus rho, and that gives us a 1. We had a 1 left over, so we have 1 plus 1 over 1 minus rho. So that's kind of fairly clean. So that's kind of delicious, right? So we had this one simple parameter, which is the innovation probability. And it turns out we get a power law that's governed by that innovation probability. So you can see, and I'll have it on the slides, but let's look at the limits, right? So if you're innovating all the time, rho is going towards 1, right? So probably the next elephant being a different flavor is close to 1. So we get a very strange exponent, right? This is 1 plus 1 over 1 minus something that's close to 1. So this is blowing up. So we're getting a distribution that falls off very steeply. And you'd have to kind of do the whole thing again, actually. If the innovation rate is 1, then we know what the distribution is, right? So it's just that there's a delta function at 1, right? Every group is of size 1. Everything is different. Everything is special. Everyone has a medal. They're all different, right? And right? So that you'd have to do it again. You can't. But you can see how it's tending towards it. It's getting this really steep distribution, which looks like a delta function. At the other end, when rho goes to 0, so new words appear now and then. New cities start now and then. You know, very kind of cartoon version of it. Then we get close to 2. Which is super duper because 2 was one of our interesting numbers, right, for exponents. That's where the mean is about to explode. I actually first found out about this from Krugman. I don't know if you know Krugman, right? He has a Nobel Prize. Yeah. Wow. They just said, here, have one. But Krugman, I guess, main thing is writing in the New York Times. But he was at MIT for a year before he was poached by Princeton. And actually, a person who was in this course, his father employed him at MIT, which is a very tall person. Unmistakably tall, huge person. All right. Anyway, he was in this course, and he said, yes, well, because I said, I sent an email to Krugman saying, I read your book. What is the reference? Because he didn't quite have it in there properly, you know. He said, it's this, it's biometric, 1955. And so I'm proud of myself for getting an email. I said, oh, my father employed him. Okay. I mean, you could obviously go through all scales. Anyway, so yeah, but his complaint about it was that he mentioned something in the email. He said that this limit's a bit funny, right? It's a totally great limit. But this limit is a little funny, that as the innovation rate goes to almost 0, that's when you get the thing that seems to match the real world, right? So gamma equals 2 is alpha equals 1. But on the other hand, you know, new cities aren't born every day. It's not. It's the right end of the limit.
Yeah.
Yeah. So real systems have to have some balance of innovation and replication, right? They have to have some balance. And I've always thought it'd be quite interesting if you could quantify that for a culture or for a city, whatever it is, or for a university. Right? What's the, if you look through time in some way, you get to quantify it in some way. What's its rate of, how's its evolutionary story going? Is it kind of bubbling with innovation, or is it, you know, stagnant? Can you quantify that? Anyway, this little model beautifully encodes those two things. Okay, so as I said, it's a micro to macro story. Right, we really looked at the mechanics of this thing, and these pieces of, well, this is the measurable outcome. How are we doing? Trouble?
Talking about
Yeah. I'm sorry, I just got myself a little confused. As gamma approaches 1, that means more innovation.
Yeah, so let's try it again on this slide because I spoke ahead of myself. This is the measurable macro. This is the micro piece that, you know, in principle measurable as well. You go and look at the thing and you see how many times a new package is appearing, or, you know, in the Linux thing, or new words. Maybe, you know, you could look through. You could simply calculate how many unique words there are in a book. Do that. You have to then. That's one way of doing it. You find the number of unique words, but it doesn't. Then you have to look at how the words appear. And if you do that, then it doesn't follow the same, you know, this very simple model.
You need to pick the right time scales, right?
You mean for a book? A book is just a book.
Row. Like if you have the macro version.
So the idea is row is what you'd have to check for. Yes, you're right. So what you have to check for is that row, if it matches this model perfectly, row would have to be not changing with time. And I said that was something that could be, you know, messed around with. You could do that. Row could have some time variation. The innovation rate speeds up or slows down, and, you know. Right. So if you want to check if it's exactly this model, you'd look at different time scales to see that it is in fact stable.
Yeah, models.
Yeah. Right. So if you look at the first half of the book versus the whole book versus a quarter of the book, you'd see that the innovation rate's not changing, which is not true. These are the things I said. So rho is approximately 0. It's a low innovation rate, right? So rho is the chance of getting an elephant with a new flavor. Then gamma is approximately 2. This is a wild distribution. Very nasty. It's certainly got infinite variance. And for rho approximately 1, when we have this incredibly high innovation rate, then we have this delta function type spike. So, you know, overall, it's, you know, really a beautiful, simple model. And of course, it's not right, but it's a very simple model. It's very transparent. It has one parameter. It's tunable. It's a mechanism that's tunable. Produces a family of outcomes. And we will talk about them of being these different, this is sort of tunable universality classes story, right? So there isn't actually, it's not as if this model produces gamma equals 3 halves, right? We'll see that the treatment by Barabasi and Albert in 99, they didn't really put in a innovation rate. I mean, they did actually, but they didn't explicitly have one, and they got out gamma as -3, right? They just got one thing, which suggested there was, you know, maybe just this very special universality class. It actually didn't match up with the real world, but it's beguiling. And then I remember asking Barabasi at the Coyote Cafe in the Santa Fe if there were different, before I knew about this, if there were different universality classes, and he said, yes, we have a paper that, you know, it turned out to be in Physical Review Letters. It turns out to be all wrong, but it looked like you got different exponents. It turns out that actually all collapses back and you still get the -3. But there are ways to show that in fact, and it's very clear from this work, that gamma, there isn't a special gamma, you know, that it can be tied to a simple mechanism. That's a really fundamental question, right? Which one's the warm one? Yeah. All right. Few other pieces. So Zipf's law, we had this round the other way, right? So this is the size of the rth ranked object decaying as out of the minus alpha. And we have this connection between the two exponents. Alpha is 1 over gamma, gamma minus 1. So gamma equals 2 corresponds to alpha equals 1. And that's sort of in keeping with a lot of rule. It's not exactly true. So in fact, particularly in words, and you'll see this, there's a break in the scaling. That's actually only really been noticed in the last 10 years and talked about broadly, but it's there. So we see, but roughly we see an alpha equals 1 to start with. Lots of systems kind of have this, roughly, not everything. So it's low innovation, and I mentioned our friend Krugman. All right. And it's still possible that other very different mechanisms are at play, and that this doesn't, because there's a randomness to this. There's not, doesn't have a big, great optimization feel. And we'll get to this later on with Mandelbrot saying he thinks this is terrible. Simon equally thinks Mandelbrot's work is terrible, all right, which is fun. So you have to look at the details to see, look at your system, how it evolved, see that this, what you claim for a mechanism is actually the mechanism. This seems a very facile point, but a lot of people have over time said, here's some power law size distribution that describes the system. I have a mechanism that produces that power law size distribution, therefore it's correct. Which is a good start, but okay, well done, pat, pat, pat. And then now you have to go and look at, show me your mechanism is really at play. Really obvious, but not well pointed out. All right, let's do one other piece. So we had, it's very similar to what we did before. We had just for the number 1, this is some fun stuff here. So rho for the, we're adding a new group of size 1. We get a row here, blah, blah, blah. So we're going to replace that m1t by just little m1 times t. That's really what's going to happen in here. And we're going to get rid of these expectations and replace that by little m1 t plus 1. There it is. And little m1 times t. Those guys are going to cancel again. We'll get little n1 on the left. These t's are going to cancel, and we'll have rho minus 1 minus rho times m1. Boom. And you see there's just m1s in here. OK, so that's exciting. So we can mess around with this. So I'm going to put this guy over here. There's going to be n1, so it's really going to be 2 minus rho times n1. And we'll put it down the bottom. So there's a 2 minus rho and a rho on top. So n1 is rho over 2 minus rho. So this is the, so again, n1, the total number of groups of size 1 is equal to n1 times t. So we have to multiply by t again to get the whole thing. That little calculation that we had before this piece will come back. OK. Yes, that's it. OK, so you can see as rho goes to 0, this kind of plausible, realistic thing, this is going to 0 over 2, so that there don't seem to be many. So if you actually count up the elephants in the groups of size 1 and compare them to all elephants, there aren't so many of them. But if you look at groups, and you count how many groups out of all groups have size 1, then it's really this number, little n sub 1 divided by rho. And so that's this bit here. OK, so I've said this. So we have this rho t. This is the number of distinct elephants, and the calculation is really over there. The fraction of unique is going to be the total number, 1 divided by rho t. So it's 1 over 2 minus rho. Sorry about this. I'm going faster. This is rho over 2 minus rho. You divide it by rho, and you get 1 over 2 minus rho. So now this is fraction of groups that are of size 1. So as rho goes to 0 here, we get a half. So a half of your distinct flavors. So if you take all of the words in a book, typically a large book, and then just, so the just gets one slot. So there's a the here, and here, and of here, right? We're not showing how big they are. We're just going to list the vocabulary for the book. And then we look at the ones, we have numbers underneath them that tell you how big they are. And we count the number that have size, that appear once, the hapax legomena. And there are half of them, right? Half of them will be unique. So that's kind of fun. Right? Half of them will be unique. And you actually do see that, in fact, for real distributions. You can mess around with this and look at the number of ones that appear twice, and you'll get a sixth for that. This is at this limit rho equals 0, the low innovation rate. So the model is doing very well at both ends of the distribution. This is a very odd thing, right? It's doing well for large k and very small k. which is kind of unbelievable. And I think, yeah, let me show you Simon's little comparison he made with actual data, which is very risky, as I've said, very risky. Very scary thing to do. So, number of unique words divided by the number of words in your vocabulary. That's, and you're asking about this, right? This is a very simple thing to do. For Ulysses, at least the version he had and the graduate students that counted the words, 0.115, right? It's easy for us to do now. You still tell a graduate student, no,
Yeah,
I mean,
one grad student.
who goes beep, 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 and it's done. Anyway, so he has this nice little table, and he estimates the number of words that appear once, and this is the real number, and this is the estimated number using that formula, which is pretty good, right? It's pretty good. And the scaling is pretty good as well. So there's a lot of excitement there. So I'm going to start with the catchphrases on this connection into Mandelbrot's work on Thursday. It's a highly enjoyable bit of madness. But anyway, so there you go. It's a beautiful mechanism, rich gets richer model. It's everywhere, and it's what underlies half of the work, if you like, that's been sort of that founded complex networks. And it's a real thing. It's a real thing. All right? Big deal. Yeah. So you want to be out in front? Accumulating the wealth is basically the story.